Hello, everybody, and welcome to another session of PyLadies Amsterdam. For those of you who are joining us for the first time, we are on a mission to promote, educate, and advance a diverse Python community through outreach, education, conferences, events, and social gatherings. Thank you for joining us today. Hope the session will be useful and inspiring for you. Today we have Emma Beauxis Asalet. I hope I pronounced that good enough. Who will be talking about Easy Fairish, the basics of classification and bias. Emma has a PhD from Utrecht University and a master's in computer science and communication. She's currently assistant professor of ethical computing at the Free University Amsterdam, the FU Amsterdam. Emma, whenever you are ready.
I'm as ready as I can be today. Thank you
Great.
for the kind introduction and attempting to pronounce my name. Just call me Emma from now on. I'm happy to be here. This is going to be a workshop really for beginners. I'm going to try to keep it as simple as possible, considering it's also the end of the day. And the program is that we're first going to have a few slides to introduce basic concepts, and then we're going to do some Python code and exercises. There are 3 notebooks that you can find on GitHub. You can find the links there, and then you can make your own copy to edit it or download it to have it in your favorite framework. So let's start. Yeah?
If there's questions, you feel free to write on the chat. If you have any question at any time, please do make your questions. You can also unmute yourself and go ahead. So please feel free to make questions during the session.
Thank you. Yes, please feel free to do that, especially if something isn't clear. And so let me reintroduce myself. This is a classification of myself that was done through a system called ImageNet Roulette. It's a classification system that was trained on images connected from the internet, from the crowd. And it's quite a famous work from Kate Crawford from the AI Now Institute and other collaborators, where they use these data sets from people who made labels on images quite freely to build a classifier that can classify people in particular. And there were a lot of offensive classes. And the one I got, which is not that offensive, is that I'm an eccentric person, a flake, an old bull, and a geek. And of course, you're in the next hour, you'll see if that was a classification error or not. But that's an introduction to tell you about the risk that we might encounter when we use AI systems without checking them for biases and for errors. So we classify about a lot of things today. And there is this well-known example as well from, I can't pronounce her name, and Timnit Gebru and other people. And they studied a classifier that was detecting the gender of people using an image of their face, and they found that it was making much more errors for darker skinned female and darker skinned people and female in general as well. And that's a form of bias. When you have more errors for certain populations, you can say that they are discriminated against. And this is exactly the kind of bias we're gonna talk about today. So there are random and systematic, random errors and systematic bias. Both have serious implication. You can have, of course, the same level of errors and too many errors. But today we're going to talk about the systematic errors that are higher for other people. And we're not going to talk about whether you should classify people or any other thing in the first place, like with this ImageNet Roulette. So now what you see on top of this is this image of faces classified by ImageNet Roulette. And we can see some offensive labels again. So black person is a rape suspect, for instance. And today we're not going to talk about this kind of other ethical issues. We're just going to focus on the errors. And to show you how far it can get, if we don't inspect the errors, we might end up having a system that seems to work, and it might just reproduce our own biases. So this is a story from the early 20th century, where these two images that you see were from a textbook from pseudoscience domain that back in the time was considered science, called phrenology or physiognomy. And with this classification system, it wasn't using any AI, but just human vision. They tend to classify people also in categories to know how intelligent they were, if they were going to be a good or bad husbands in this case, and all sorts of other prediction about people. And it was disproven later on. And how was it disproven? Exactly by looking at the errors and biases. So that's to encourage you once more to dig deep in the errors and the biases. Otherwise, we can have this kind of classification system that are not reliable, if not worse than that, that could create discriminations at large scale and just reproduce our biases. And we might not be able to notice it if we don't look at the errors. And so that's one more motivation for today. We must look at those errors and bias to not repeat large prejudices at large scale. And if you're more well-versed I mean, you can rely on the experts to do that for you. And the experts might tell you that they are just engineers and it's not their job. So that's also why I wanted to make this workshop for beginners, because I think everybody should have a say into what are the errors and what are these biases due to more errors for certain people, because we can't always rely on the technical people to inspect them for us. And on the other hand, I again want to motivate people who are not technical experts to inspect it, because even if we're not nerds, there are still some basic checks that we can do that should remain accessible to everyone. And that's the ones we'll discuss about today. So after this motivation and introduction, let me explain a key concept about classification errors. If there is one thing you'd remember from today, I hope that would be this slide. So what is a classification error? So let's say we have a group of people that belong to class A, that's the circle you're seeing, and we want to classify them. And there would be some of those people that will be classified into the wrong class, let's say class B. And those are errors. So far, it's quite simple, but bear with me. These errors are directional. It's an object from a true class, an original class that is misclassified into another class. So an error that is an element from class A classified as class B, it's not the same as an error that is from class B and classified as class A. So here we have the errors from A to B, so to say. And then we can see now what has been classified as class A indeed. And a part of it has been classified as class A wrongly. So they come from another class to class A. So they're called false positive from the perspective of class A, but I don't want to bother you with this terminology. And then there are other elements that belong to class A and are classified into another class. And well, they're traditionally called false negative from the perspective of class A. So this is one important thing to remember when we look at the classification errors. It's not just the number of errors, it's also what was the true class and what was the class it was classified into. And then about the definition of bias regarding errors, there are several definitions we can see. Kind of a generic one is that if you have systematic errors that occur between the prediction and the truth. Then there are biases that are systematically different between the classes. So for instance, here you can see that for class A, there are a lot more elements that are missed than for class B. And we can say that for that reason, class A is biased against. And then there is also systematic errors between groups. So now we look at elements that all belong to the same class. Let's say some are female and some are male. And if there are more errors for the female, we can say that this group is biased against. And finally, another definition of bias is about underrepresentation. Perhaps in my ground truths, I have less female than male. Normally in the general population, it's 50-50. And female are underrepresented and they are biased against. I'll talk also a little bit in the code later about this bias too. And then there can be also a class that is underrepresented. Maybe my class B, I have much fewer items than from my class A, and it's underrepresented and it's biased against. So when you train a model, if you have underrepresented groups, the chances that you make more errors for them is higher. So finally, the last few slides is about measuring errors. How do we do that? We use a test set. So it's a data set that contains example of what are the correct classifications. So here, let's say we're classifying sad and happy customers. And we have a data sets where we have examples of both the sad customers in red, happy customers in gray here. And the errors is when you don't classify them in the right class. So we have two classes that's called binary classification. And now let's, for the sake of example, let's imagine we have a very, very simple classifier. We use only one feature, one variable about our data set. That's just for this example. Let's say we measure how large is the mouse on their face. And perhaps sad people have smaller mouths, happy people are smiling, they have larger mouths. And we can see what is the distribution of people sad and happy regarding the length of their mouths. And if you're lucky, that's something you can see a pattern in. The happy people have larger mouths. So let's say we do a very simple classifier using just one variable, one feature. And what we can do is make a threshold on it. And let's say if the mouse is higher than a certain value, we classify them as happy and below as sad. And here we can start counting the errors for a test set. So if we make a model where this would be our cutoff point or threshold, we can see we'll have one error for sad people, they're classified as happy, and 4 errors for happy people, they're classified as sad. And here, let's say I make another model, and this one, it uses another cutoff point, and I count the errors. I see I have much fewer errors with that model. So I might select it. But the tuning decisions, so the choice of model, it depends on the use cases and on the requirements of stakeholders. So let's say I have another use case about the same distribution, but this time it's classifying donuts as damaged or not. And it's a real life use case. My uncle has a donut factory and he does that literally. He has a machine with computer vision that check if the donut is in a good shape or not. And for my uncle, he doesn't want to throw away too many donuts. He doesn't want to throw away the undamaged donuts, of course, but also some donuts are a little bit damaged, but it's okay, it's acceptable. So in that case, my uncle would choose another threshold oh, not this one, for instance. I'd rather choose this threshold, because this one is worse for my uncle. But if my uncle was selling a absolutely luxurious French donut, he might still want to choose this threshold to make sure he only has the top quality donuts for his luxurious French clients, because I'm French, if you can hear it. Okay, so that's to give you this introduction, and you can choose between different models, and you have a trade-off to make between the two types of errors in that case, so the direction of errors. You should have more errors from damaged classifiers and damaged, or the opposite direction. So that's all about the kind of trade-offs we have to make when we inspect models and we choose the right model or the right tuning parameters to balance the errors, and therefore the biases as well. So you have to be aware also that when you do that on a test set, it has a certain class proportion. So here's that example with happy and sad. And maybe in real life, suddenly I have much more sad people that appear. And then in that case, I might choose another model or tuning parameter. So these are also the kind of problems we have to look at when we inspect errors and biases. What is the mass for each class and each population? Because if you have more of one, it creates more errors, certain errors and not others. Okay, so here's a recap of how we estimate errors for classification. We take a sample, a test set. We run an AI on them, and we count the errors. And then we use those errors as estimates of the errors we can expect in practice. And all this system is made on samples of data sets. We have a test set to measure the errors. To make the classifier, we have a training set. It's also a sample of data set. And then we apply it in real life on real life data sets that are sometimes called target set. And you have to choose carefully, is it a random sample or not a random sample? Sometimes in the training set, you might decide to make it a non-random sample. So with a random sample, it would represent the proportions you expect in real life. But for the training set, for some classifiers, sometimes it works best if you don't use the proportions in real life, but you balance your classes. We're going to see this also a little bit in the code. And finally, so in real life, the training set is fixed, but you can try different test sets to represent different target sets. And you have to remember that these are all samples. And if you use a small sample, you can have high variance. So it means that, let's say you take just 10 elements, you classify them, maybe you see no errors at all, and you might think your classifier is perfect. And then you take another sample of 10 more people, and there you see you have a lot of errors. So when you estimate the errors to expect with the classifier, you have to also be careful to estimate them with a sample that is large enough. And finally, if you want to use one test set as being representative of the errors you'd expect in practice, if in practice you select small batches of people or other elements, you can also expect a lot of variations of these errors in this small data set. So those are just a few elements to keep in mind. I hope it introduces the basic concepts for the code that we're gonna see now. Yeah, the class distributions also can vary randomly or not. So now in real life, you might have cases where you use an AI in practice and you end up seeing the numbers. So in that example, let's say you count the types of cells over time, and it's the AI that detects your kinds of cells, and you want to know, okay, in this number of cells that the AI has detected, how many errors can I expect? And you can see the detection over time and some variations here. The blue cells, they suddenly increase, and if the blue cell increase, maybe their errors increase too. And when we see the purple cells, they also increase, maybe it's just about the errors. So this is the kind of problems we're going to start tackling. how should you make test sets to or sample test set or inspect the errors to know how many errors to expect in real life. So that's it for the slides. Now we're gonna go to the code. I can take questions while you set up also your environments, but in the link you find in the chat, you can find the links to 3 notebooks. There will be 1 exercise per notebook, and there is also the notebooks with the solution. So if you're really not so comfortable with starting to code right now, or if it ends up being too difficult, you can have a peek at the solutions if you want to. And so you can click on the link to open the notebook. You should be able to make your own copy to change it. You can go on File and then save a copy in Drive. You can also download the notebook to open it on your local computer. So if you have any questions so far, please be welcome to ask them.
If somebody has questions also on working with Collab, we might be able to help you. We were wondering, I think you need to have a Google account, but maybe not. But if anybody needs help, feel free to ask. Yes,
feel free to say it, so then we will know for next time.
Yes.
But I find Collab quite easy because you don't need to install any environment to work on your laptop. So that's why I chose it.
Right, and you also don't use the resources of your laptop, so I'm guessing, I don't know how do you say powerful the machine behind it is, but you could try to.
And the free version is not all powerful.
Okay.
but for this exercise, it's enough. Indeed, if you have larger data, and it might not work perfectly fine. Thank you for the tip, Marissa. I'll have a look at it. All right. So let's get started with the code, unless somebody says something. Stop me now or later. All right, so our first notebook has 8 main sections. The first one, super easy. It's loading basic library and loading the data. For now, I'm not going to say what's happening in that cell when we load the data. I ask you to ignore it. We'll talk about that a bit later. We're cheating a little bit today. But so basic library, Panda and NumPy, and that's for manipulating data and data frames. Matplotlib is for the visualization, and Seaborn as well. This one is to not display the warnings. I find it very handy. So actually I don't. Here we have loaded the data, and we're going to check what kind of data we have. So we have loaded data in the form X and Y. So we have 2 data frames. And traditionally in machine learning, X is the name given to a data frame containing the data features. So each row is an element to classify, and each column is a data feature that describes that element. And Y is a data frame that contains only 1 column, and these are the labels that we need to predict. So what would be the true classification? In our case, we have 2 classes. It's a binary problem, and they are represented by a label that is either 0 for class 0 and 1 for class 1. I'm not going to say now anything about what it might represent, because first we're going to work on on an abstract level with just a few features, and just to see what we can get. But you can imagine those classes can represent people you select for university, yes or no. Do people have an illness, yes or no? Should people be put to jail, yes or no? All sorts of classification. And in our features that we're seeing here, we have 4 features that are numbers and they don't have names because we stay at an abstract level for now. So 4 features and a feature that represents the gender. So 1 is for female and 0 is for male. And here we see our data frame, so our 4 features and our gender. We can see we have 4,000 elements, 4,000 rows, and our 4 columns. And here we see our labels. It's either 1s or 0s. And again, 4,000 elements. So this is the data set we work with. It's very important to always inspect your data to see what's happening. So that's why our next cell is a visualization of the data set. So I copy all my feature into a new variables to which I will add the class label. And then I will make a scatter plot matrix, which is a series of 2D visualizations. Series of 2D visualizations that would show each feature as the X or the Y axis. So here we see on this row, on the Y axis is my feature 0, and on the X axis is my feature 1. And here in this upper triangle, we can see the different distributions of the classes. So the color represents the class. I don't want to go too much in the detail of the visualization, but if you have for the code, but if you have questions, just let me know. So here I can change what is used as the color code. So the hue is for the colors, and here I use my column class to put the color. And so here we can see the distribution of the class 0 and class 1 over all the features, and also over the gender here. So here is for gender 0 for the male, gender 1 for the female. So we can see the distribution. It's a lot of overlap, so it's a little bit hard to visualize. But we can also see with the histograms there what are the sizes for each class. So this number of items here, because it's on the diagonal. So on the diagonal, the y-axis is the number of items. So I can see that I have much more male than female. And I can also see what's the proportion of class 0 and class 1. So the class 1 is in green, the class 0 is in red. When they overlap, it makes this gray color. A little bit hard to see, but I'm telling you. So here I can see I have a complete overlap. So for the males, I have as many elements in both classes. And for the females, I can see I have less elements. And also the proportion of class 0 is much smaller. So that's our visualization. I hope that was clear. And now we're gonna see how we can classify this data set. It's really just a few lines of code. So the first thing we need to do is to split it into training and test set. And that's because we use one part of the data to build a model and the test set to evaluate it, to measure the errors. And for that, there is a simple function called train test split that splits a data set into training and testing. So this function, they typically work with this X and Y variable, where first one is the feature and the second one is the label. There I tell it what is the proportion of data I want to use as the test set. So 0.2, so it's going to take 20% of my data points and put it as test set and the rest as training set. And it's going to make a random split. If you want to control the split, the exact split, you can use this random state variable. If I specify it, now each time I run this line of code, it will give me the same split. If I want to make it random, I have a new split each time. I just have to remove that, like this. And then this function is gonna output 4 variables where I have part of my ground truth as train set, part of with the feature, part of it for the test set, and then part of the label for training and part of the label for testing. So I make this split X into 2 parts and Y into 2 parts. And this is what we're going to use to make a classifier and then test it. To make a classifier, it's amazingly easy. I can import them from scikit-learn. There are other libraries, but today we're using this one. This is a naive Bayesian classifier. There are different types. I'm going to call the Gaussian naive Bayesian. I'm not going to explain very much how it works, and I think that's also part of the exercise, is that it's so easy that we can use models. And here you see 2 lines of codes. We don't even have to put any parameters. We don't have to know what we're doing, but we can do it. So that's what I'm going to do now. Maybe the other classifiers I'll explain a little bit, but we load this type of algorithm, the Gaussian. It's a kind of a Bayesian algorithm. So we load this Bayesian algorithm, and then we make a model in just 1 line of code. I call this function, this algorithm, and with fit, I tell it, now you fit the model. So here I have the kind of model I want to use, the algorithm, and then I run the algorithm with fit so that it builds a model, and it builds a model that will take the features and that would use this feature to predict this label. Ignore this 0 here, as I put it to avoid some warning, and then I disable the warning, doesn't matter. But it works with or without it. So here in 1 line of code, I take my algorithm and I make it build a model, and that's it, we're done. But then how well does that model work? We have to check. And for that, there are many different metrics we can use, because their errors are bidirectional, and you can make different forms of error rate, false negative rate, true positive rate, precision, recall, accuracy, F1 score. There are a lot. And I don't want to bother you with the equations for them. And later on, we're going to see a visualization, and I hope that with it, you'll be able to see any kind of error rates without having to know the formula. So that's why there's no formula in this tool. You're lucky. But we're gonna use still one measure that is quite well known. It's called accuracy. And formula is quite easy. Accuracy is the number of correct classification on the total number of items. So it doesn't matter the direction of the errors. You count what is correct, what is not an error, and it's the proportion of error on all the elements you've classified. So you probably heard 90% accuracy. It means 90% of the elements you classified were correct. For the 10% of errors, we don't look at the direction, if it's from class 0 to class 1 or class 1 to 0. So it's a simple metric, we just have one number. So with this line of code, we load a function that calculates accuracy. And so what we do now, we use our model. It's again very easy. Now I call my model that I made here. And with this function predict, I give it another data frame with data points and data feature, and it's going to predict their label. And if I want to check the accuracy, I use this function, accuracy score. I give it the true label, the labels that were predicted, and it's going to count how many of them do not match and make this proportion. So here with this simple classifier, I have 63% accuracy. It's not great. But when you try to do better with another classifier, and it works the same, it's amazing. Just a few lines of code, you build a model, you use it, you test it. So this time I'm going to call another algorithm, a tree kind of algorithm. So this kind of algorithm is going to make splits on a variable, like what I showed you with the length of the mouse. It's going to make a split to separate your two classes and make two groups. And then for each group, it's going to take another variable, perhaps the same, and make another split to try to separate again the two classes. And it's going to go down, making splits and then resplitting and resplitting until it stops, because it ends up having a good little splits where you have almost the same class each time. Very short introduction of tree. But even if you don't know what you're doing, you can still use it without putting any parameters. Just load the decision tree classifier and your algorithm. You take your algorithm, you fit it on your training data again, and then you have a model that is built with all the splits that are chosen. And then you use your model to predict the labels for a new data set. And again, you can check the accuracy. It's 1, 2, 3 lines of code to use a classifier, and one more to check its accuracy. And here with this one, just out of the box, we already have 81% accuracy. So we're just making 20% of errors. It's already much better. So at this stage, we can say, okay, I'm gonna use the tree classifier. But then maybe there is a bias. Maybe female have more errors than male. And perhaps this classifier is good, but it has a huge bias. So here we're gonna check the biases between male and female. So to do that, we have to filter the data to split it between male and female. So this, for you to understand the code, this line, it takes my test set that I had, and it's taking the variable gender. And here with 2 equal, it tests if it's equal to 1. So it takes the column for gender and tests if it's equal to 1. And the results, as you can see, is a series of true and false. And this will tell you if yes or no it's a woman or not. And I'm detailing this because we're going to use it to split our data in two. We're going to use it here in this cell. So with this line of code, we take our Bayesian model and we ask it to predict the labels, this time just for the female. So I take my data frame, my test set, and here in this bracket, I give it this test. And with the series of true and false, it's gonna give me back only the rows that are female, only the rows where the gender is 1. So by doing this, I ask my model to predict the labels only for female. I store it here. And then I can check the accuracy for female. So here's the labels I predicted. Here I take the true label from a test set. And again, I use the same filter because it's the same order of first row in my X from my feature data frame is correspond to the first row in my label data frame. So I use the same filter here. And this time I'll get the accuracy only for female. If I want to do it for male, I just need to change the test here I'm making. This time I want the gender to be equal to 0. And I also have to change it here when I filter my labels. So now with these lines of code, then I can print the accuracy of male and female and male. And I can see that I have actually much more accuracy for female than for male. Once in a while, we discriminate against them. But it's a little bit hard to check. So I made a little function that I'm not going to detail. It does that, the same lines, plus it rounds the accuracy. It makes the difference between male and female, and it also makes the mean of accuracy. So now if I run a quick check, I just have it in one line of code. This check accuracy is a function I made for us to use. So here I compare my Bayesian model with my tree model. And I give it my function, the test set, and the test I need to make to filter out male and female. So here I can see, interesting, yeah. I can see the accuracy here for male and here for female. Here it's the difference between those two numbers. And here is the average between those two numbers. So when I read this line here and I compare it to this line there, I can see again that the accuracy on average is lower for the Bayesian model. The bias is also higher, so it's definitely a worse model. So we can select this model, but we see that we have a bias. we discriminate against male and female. So we want to solve that issue. How are we going to do that? Something that we might think about very intuitively is to say, okay, then if it's sexist, I shouldn't use the gender. I should remove the gender and train my model without using the gender. And that should not let my model learn to be sexist. And this is what we try here. So here we have the same lines of code, except that we train our models, both the Bayesian and the tree. This time we use it, we use our feature without the gender. So that's what this piece of code is doing. Take your training set and here you drop a column with gender. So now I can train both the Bayesian model and the tree model without using gender. And again, I can check the accuracy. I also have to drop the gender in my test set for it to work. And I can see what we obtain, and we can compare it to that. So a nice function with Collab is that I can press this button here. It's going to make a cell on the right side, and I can look at my cell on both sides. So here I remove gender and I retrained my model. And I check the accuracy again. And what do I see? So for the Bayesian classifier, I have no more gender bias. It's almost zero. And the accuracy has decreased a little bit. So you could say, okay, that's a trade-off. Sometimes indeed, you can see that. And what do I see for the other models? This time we have a completely different effect. Similarly, the accuracy has decreased, which is not good. The bias has decreased as well in absolute values, but the bias has changed direction now. So instead of being discriminative against male, now it's discriminative against female, because the accuracy for female here, it's lower than for male. So we have very different effect. In both cases, we see that we reduce the accuracy, which is not very good. And we're gonna explore what did this happen in the exercise. But we also see different effects. In some cases, you might indeed reduce the bias. In other cases, absolutely not. You can change, you can even reverse it, you can increase it. So generally, removing the protected attribute, that's how they're called, like gender, race, or age, or nationalities, and not training your model using those, it's not guaranteed that it works at all. And there are different reasons for that. We're going to see one reason just now in the exercise. And at the end of this notebook, I'll tell you a few more reasons. So first exercise, it will be about repeating this line of code I'm going to show. Here I will make a scatter plot matrix only for female and then another scatter plot matrix for male. I use a color palette. I'll show you where to use it later. That contains 4 colors. They're the colors I want to use for female class 0, female class 1, male class 0, male class 1, 4 colors. And they're stored here. And here I make my plot for female. Here I take my data frame of feature, my X. I filter it to keep the gender that are equal to 1 only, so the female. I use a copy. I don't want to bother you with too much technical detail. It's because later on I will change this data frame. And if I didn't use copy, when I change this data frame later, if I would change both this data frame and the X. But ignore it for now if you want to. So here I make a copy for a data frame only with the female. And I add a column with the class label. that I take from my data frame Y, and I filter it again using the same filter, the list of is it female, yes or no, that I can get from these features. And then in just 2 lines, I can plot this beautiful scatter plot matrix. So I take my data frame is just female. I drop the gender because I decide I don't want to plot it, but it would work even if you don't drop this column. The color, I tell it to put different colors depending on the class, so class 0 or class 1. Here with a palette, I tell it I want to use the first 2 colors in my palette. The markers here is to make the points smaller. And here I plot again a scatter plot matrix where we have all the combination of my 4 features as a X and Y axis. So here on the first row, my Y axis is my feature 0, my X axis is my feature 1, and on the diagonal, I have a density distribution. So these are exceptions on the diagonal. Now the y-axis would represent numbers of items, and here the x-axis would be feature 0. So here, instead of plotting feature 0 against feature 0, we plot feature 0 and the density, so how many items per each value of the feature. So that's a scatter plot matrix. We have used it to display only the data for female. And here comes the exercise. It's to make the same scatter plot, but instead to display male data. And to select male data, this time we want the gender to be equal to 0. And then the question is, now if you look at the 2 scatter plot matrices, can you think of an idea of why removing gender has not solved the issue with bias for the tree model? And then if you're done with that, the next step would be to look carefully at the visualization in section 1 in this notebook. Sorry, it's section 2, apologies. This visualization, and in particular this cell here of the visualization, and think about other ideas that could explain the gender bias or how we could solve it. So that's your exercise. I propose we take 10 minutes to do it. So I'll see you at 7:32. I'll be here also to answer questions. I can see with some students sometimes if other students ask questions when they're focusing on something else, it disturbs them. So I suggest as the protocol, I'm here, I can answer live questions for 10 minutes. If you want to focus on your code, just disconnect your sound and come back in 10 minutes.
All right, let's take everyone indeed around 10 minutes, and you can still use the chat, and the rest I want to work in silence indeed. Just mute yourself from the world. So we still cannot look at loading data, right? We cannot cheat.
Oh, yeah, of course you can cheat. Of course. But if you understand these lines of code, then this exercise, you can answer the question too directly. Okay, 2 more minutes. So I'm gonna give a quick peek into the solution. Okay, time is up. Time's up. Back to the notebook. So here was the solution. It's not very complicated. It's copy pasting the same code as above. I renamed this variable. I changed the test. Now this time I want the gender to be equal to 0 to find the male. So that's how I get the data for male. And then I reuse it in the same function as before. I call this data this time. This is where I changed the colors to get the blue colors. So now we see this scatter plot matrix, and we have the two, one for male and one for female. If I want to compare them, I can put them side by side. Well, of course, one is going to be bigger than the other, but we can see how are my two classes distributed, whether it's a data point for male or female. So here, if we see this this first cell, we can see that we have a quite different distribution. So here's my feature 1, here's my feature 0. And I can see a cluster here for the class 1, the light blue for male, and a cluster like this for the class 0. And when I look at female here, I have a totally different pattern. I have 2 clusters for the class 1 and 2 clusters also for class 0. And you can go on and compare cell by cell and see, for instance, this next cells, I have one cluster this shape and another cluster in the middle. And here I have a totally different pattern. Why? Does it make sense? What's happening here? So now I have to make a revelation. This is fake data, but I guess you probably have guessed it before. It's just simulated data. There is a piece of code that simulates patterns for me. And that's the data we've loaded, it's simulated. So this simulator of data is meant to try out classification problems. And in our case, I generated different patterns for male and female on purpose to make you do this exercise. But what does it represent? In real life, it represents the case where male and female do have different patterns and different ways to express how that they belong to either classes. You can find example of that, for instance, in medicine. Let's say female body responds slightly differently than male body, even if you have the same condition. The female body might have different blood sugar levels, different blood pressure. I'm not a doctor and I will not tell you an exact example, but for heart attacks, for instance, men and female would express the symptoms differently. So there are use cases where male and female would belong to both classes, but they would have different patterns. For facial recognition, perhaps the patterns in the data points as you observe them with the camera reflected on skins with different tones, then you'd have different patterns as seen by your camera for darker skin and lighter skin. So that depends, of course, whatever you're trying to classify, but it can be the case where both your subpopulation, they have different patterns actually. And if you'd want to make a good classification, you have to consider the gender for that reason, because without the gender, you can't interpret the patterns in the data feature properly. So that's one reason why removing gender did not solve the bias issue. The behavior we've seen with the Bayesian classifier, it seems to work better. It probably picked up a generic pattern that might fit both male and female, but miss a lot of data points anyway. It's slightly above being a random classification. If you classify elements at random, you have 50% accuracy, and we had only like 62%. So the impact on the classifiers depends on the model you're using, and depending on the patterns in the data, removing your protected attributes is not going to solve it. There are also other cases where there's a proxy variables. So it's, for instance, you want to not be sexist and you do remove gender and you hope you're not going to be sexist, but there might still be ways for the computer to pick up what is representative of gender in other features. For instance, it's been shown in HR and human resources that the way a female would write her CV is different than the way a male would write his CV. And even if you're trying to not pick up features about male or females, in some cases, that's what you should do. Not in this case, for instance. But even removing the protected attribute is not enough. I also want to apologize if I am very binary in terms of male and female. I understand that this is a construct and there is not only those two classes, but I wanted to make it for beginners. So there's only two subgroups. Apologies for this. Okay, so if you'd want to visualize both data points at the same time, that's what we can see here. And this time on the lower part, I put these blobs here with an algorithm that will try to make the contour of my data points to see indeed how different are my patterns between dark blue or dark red, which is the class 0, and the light one, which is the class 1. To do this kind of graphs, I had to struggle a little bit. So there is a hack where I concatenate gender and class into a single column, and I put gender would be the first number. Oh, and my interesting. I don't have my legend for it. Okay, I don't want to bother you with the details of the code, but for the most experienced coder, this would be something to reuse. So that's to explain why removing gender didn't work in our case. And now the question 3 and 4. Look carefully at the visualization in section 2. Sorry, I wrote the wrong section. So here it is. I have a little bug here on this display, apologies. And here I wanted you to look at this cell here. So once again, it shows it's on a diagonal, it shows the distribution, so how many items per value, and we have those just two values for gender, 0 and 1, missing some values there, but hey. And here we see the number of elements. So for gender equal 1, we have in green, it's the class. My legend has disappeared as well. In green is class 1, and in red is class 0. And we can see that we have fewer items for female in that class 0 compared to class 1. So it's not balanced. And we can also see that the proportion of both population, male and female, is not balanced. And that can impact how we have built our model. And maybe this is also what could create the gender bias. So in the next cell, we're going to try to retrain our model with balanced data. And that's what we're going to do here. So this time, we're going to resample our ground truth to have the same number of elements for male and female and train a model on balanced data, because it can work better. Here I have a function to resample that I load from scikit-learn as well. And so what we want to resample is the data points for female. We want more. And so here I filter again my feature and my label to select only what is about female. And I'm going to ask this function to resample both these. And it's going to pick up an element randomly and put it in my new sample. And it's going to do that with replacement. So it can pick up the same item as many times as it can happen. So it picks an element, copies it in a new data set, puts it back, and then again, pick up a random element, and so on. It does this to select a number of sample here. And here I wanted to select the number of sample that I have for male. I filter my male Here I take the shape of my data frame and I take the first value of the shape, which is the number of rows. That's what this property is. It's going to give me number of rows, numbers of columns, and I want number of rows, so the first value. And here I have resampled this with one line, as many elements as I have for male. So I'm going to duplicate a lot of my data points. And now I can see that I have 3,000 data points for my feature and my label, same as male. Next step, I concatenate the new resampled female with my sample for male. This is to reset the index to have the number of rows that have numbers from 1 to 6,000 in a continuous order. So I merged my two data sets, my oversampled female and my male. And now I have a data set that is balanced for male and female, 3,000 elements each. And I can again split it into training and test sets. So I split my oversampled data set. Oh, and this time I've put more elements in my test set. And then I can classify it. So again, I run the same kind of lines of code. I rebuild my model on my new train set, two models, and I check the accuracy. So did it work? Let's check the accuracy we had before. Removing gender, it didn't work. Up, I'll put this one on the side and then we can compare. So what do we see is that the Bayesian classifier has not improved. The average accuracy has decreased once more. The bias has increased. And it wasn't enough to balance the gender. Perhaps if I balance the class numbers as well, it will work better. That's what we'll try next. And for the tree classifier, we have mixed results. We have more accuracy, so that's better. On average, the model is better, makes less errors on average. But the bias is slightly increased. It's a little bit worse. So accuracy has increased both for male and female. That's good. But it has increased a little bit more for female than for male. So my bias is a little bit higher. So we have mixed results. So maybe it's not enough to have a training set where the subpopulations are balanced. So we can now balance also the class. So again, I have my functions to resample. This time I sample elements for class 0 female, class 1 female. Am I missing some lines of code? Oh, sorry. This is not up to date. Some issues has happened. It's not the latest version. Oops. But anyway, at least you see the code, the basic thing. You can finish it on your own. It should be simple. Here I resample for female and for class 0 and class 1 separately. I do that by testing both. Here I select elements that have both a certain gender and a certain class label. So gender 1 female, class label 0. And I sample it with the same with half the number I have for male. So I still oversample for female. Oh, no, it's okay. It works this way. That's because the male data is already balanced for the both classes. So that works. But you can also, if your male data was not balanced, you could also have oversampled them, resampled them. So now I oversample separately for class 0 and class 1, male and female. And so now I see I have 1,500 items, so half class 0, half class 1 for male and female. And again, I concatenate everything. So my data points for female class 0, my data point for female class 1, and then my data point for male that are balanced already, same number. And now I have, again, 6,000 elements. I resplit it into training and testing. And what do we see here? As a result, the Bayesian classifier, it's a bit mixed. I have decreased my bias. So indeed, that was probably the right step for this kind of classifier. But my accuracy has slightly decreased as well. And for the tree classifier, I have a bit more accuracy and also a bit more bias. So for the tree classifier, we also had the same situation as before, an increase of accuracy on average, but it increased more for female than for male. So you can wonder why has accuracy decreased with the Bayesian classifier? It's because we're oversampling, we're sampling the same elements over and over again. And with that, we run the risk of making a model that overfits. So you could think, okay, if it makes me overfit, maybe I could try again to improve my Bayesian classifier. And this time, instead of oversampling, so duplicating data points for the minority groups, you could undersample. So I have a majority group and I can remove some elements until I have the same balance. It's also an option, but this time, instead of running the risk of overfitting, you'd run the risk of underfitting. And you shouldn't do that unless you really have a lot of items. But in our case, we have only a few thousand, which is quite too few to do downsampling. So as a conclusion for this first notebook, which is one of the biggest, the second one is smaller, is that to solve bias, removing the protected attributes is not going to solve it. Maybe in a few corner cases, but in general, that's too good to be true. Then the bias you observe, it depends on the feature distribution. So these patterns you'd have for different populations, for instance. Also the class balance and the subpopulation balance. So if you have fewer items for a certain class or certain subpopulation, you have more risk that they have higher errors. And balancing the features, the balance of features, classes, and population, it has different impact depending on the algorithms. So there is not a one-fit-all solution, sadly. So that's why you should sample your training set and your test set carefully and preferably before making your AI models, because the resampling has issues of overfitting and underfitting. But as a general rule that you can start with, training sets that are balanced over classes and subpopulation might tend to work better. But the test set, in any case, it should represent the situation in real life. And that's the thing we're going to focus in the next two notebooks. That will go faster than this one, I hope. All right. So if you don't have any...
In the chat, there's two questions, but the second one, I think you answered it, but...
Yes, second question, yes, indeed. In some cases, you can think of making separate models. Acquiring more data is always welcome, but sometimes it's too difficult. It costs money to get data. Yes. What if naturally you have more than one class than the other? So for the training set, it depends on your algorithm. I could go on in the details of how the tree is impacted perhaps differently than the Bayesian classifier, but I'll need another workshop for that. Resampling, yes, in some cases, if you have high imbalance, you have very little choices than resampling for your training set. But for the test set, I recommend that you use a test set that represents the proportions you're going to have in real life, because that's how you're going to assess the practical impact of your errors and the practical biases you can expect. And that's what we're going to see in the last notebook. So second notebook, I might go a little bit fast so that we focus on the most juicy part. So let's see this notebook. So again, we load our basic libraries and we load our data, but this time the data is loaded already balanced. So here is my simulator of data. I will not go into detail, but I have 2,000 items for male and female, and the class proportion is 50-50. And then we can visualize the data. That's the same. Oh, it's slightly different perhaps than before. But it should be the same, yeah, because each time you generate data, it's another sample. So no, it might be different than the patterns before, but it doesn't matter for this exercise. But it's always good to recheck your data from time to time. So now we have seen the bias inaccuracy. That's the same lines of code. I duplicated them in case you open just the notebook, you can already run the classifier. And now we're gonna jump directly into the biases in false positive and false negative, FP and FN. What terrible terms, false positive, true positive, false negative, and true negatives. I'm quite critical of these names, and that's why I'm not gonna explain them, the terms themselves. But they're historical terms. They make sense. They do make sense, but I just know that the terminology is not easy for beginners. So I'm not going to torture you with that yet. But hopefully after seeing the rest of this tutorial and some visualization, you know the concepts and it will help you later to understand those terms and remember what they mean. So false positive and false negative, there are two types of errors, and that depends on the direction of your errors. False positive, it's classified as positive, so it's class 1, but it belongs to the other class. So the direction is from class 0 to class 1. False negative is the opposite. It's an element that belongs to class 1, classified as class 0. So to inspect the different types of errors, there is something we can do that is called a confusion matrix. Here I import a builder of confusion matrix from scikit-learn. So I will take the prediction for a female, like we did before, and this time I give it with the true label and the predicted label, and I'm going to build a confusion matrix. And that's what we see printed here. This confusion matrix is that's 2 rows, 2 columns. The first row, in that case, it represents elements that truly belong to class 0. And this is the elements, the column is what they're classified in. So these elements, they belong to class 0 and they're classified in class 0. So they are good classifications. These elements here, they belong to class 0, that's my row, and they're classified in class 1, that's my column. So they are the false positive, they're not good. And the next row is what truly belongs to class 1. And these ones are classified as class 0. Errors, they are the false negative. And these ones, they belong to class 1, classified as class 1. They're good. They are the true positives. But so to read a confusion matrix, in the diagonal, you have everything that is correct. And the other cells are the errors. And you can see the direction of errors. And when we plot the confusion matrix for male and female, we see that we have more error for males. That's from our tree. And we also see the direction of errors. For female, the false positive and false negative is roughly the same number. And for male here, we see that it's not. There are more of one type of errors than the other. So that's important because in some use cases, like with the donuts of my uncle or with detecting an illness, there are some kinds of errors you want to avoid absolutely. If you're detecting an illness, you don't want to have false negative. You don't want to miss it. If you're detecting bad donuts, you also don't want false negative. But perhaps you're also more tolerant to false positives. So that's why it's important to check this this confusion matrix. So I made a little function to plot the confusion matrix in just one line of code. So that's the same line as above. And we can check the confusion matrix for a tree model and a KNN model. Did I talk about the KNN model? No. Did I? I went too fast. Here I loaded another model, K nearest neighbor. This time I use the parameter, but again, it's just a few lines of code. I load my KNN model, KNN nearest neighbor, and I train it, same kind of code, training set, labels, and I can check the accuracy as well. And it works better and it has a bit less bias, so that's a good candidate. Yeah, it's the nearest neighbor. This network is going to look at, if you take one data points in your ground truth, you take the data points around it, the closest data points, you check what class they belong to, and then you decide the majority class. And here I told it to choose the 31 data points that are closest in the ground truth. But let's say we trained another model very easily. We don't even need to know what it does in details to use it, and it works a little bit better. So now I compare those two candidates, the true model that was working better than the Bayesian model and the KNN model. And I can compare their bias in accuracy and the detail of their confusion matrices. And it's a lot of elements, huh? It's hard to look at it. That's why I made a visualization for you, which is here. So there are custom visualizations. I'm not going to bother you with the code, but here I have, that's the function I made for you to make a visualization that shows the confusion matrix as simple bar charts. You give it a model, you give it a test set, train the features and the label. You tell it how to separate your data sets into two subgroups. So here I isolate female versus the rest. And you can also give it a title if you want. And here is what it shows. So it uses again these two colors, pink and red for female and blue for male. I know it's a cliche. Back in the time, centuries ago, it was the opposite. Pink was for male and blue for female because pink colors were more expensive, so they would go for male. Take this. But now we have the expensive colors, so pink female, blue male. And now I have 4 different bars. And on my y-axis, it represents numbers of items. And the way it works is that I have 1 bar per class and per subgroup. So for my female in red, I have 1 bar for the elements that truly belong to class 0. That's this first bar. And then I have this bar for the element that truly belong to class 1. And same for male. And then on the y-axis, I see how many of them in numbers have been predicted as class 1 above the 0 axis, or as class 0 below the 0 axis. And this way you can see a lot of information. Without reading a table, you can see a lot of error rates without knowing their formulas even. So we can see the detail of what is false positive and false negative and so on. So if it belongs to class 0 and it's classified as class C1, that's this dashed block here, and those are the false positives. So here are all the elements that belong to class 1, and here are the ones that are classified as class 0, and they are the false negative. But in essence, the errors are the dashed blocks. And you can compare now the errors, different forms of error rates. If you want to do accuracy, it's the proportion of the dashed blocks on all the elements for female. And the accuracy for male is the dashed blue blocks on all the blue blocks. And we can see that accuracy is much lower for male. Sorry, the other way around. Accuracy is the non-dashed blocks on all the blocks. Anyway, we can see accuracy is lower. Then you have different forms of error rate depending on what matters. There is something called precision, and it means in everything that you selected, how much were correct. So here I can see the precision for female. It is everything that is selected as class 1, so above the 0 line. And I can see that these are the correct ones. So the precision is pretty high. There's a lot more correct than incorrect. And if I look at the precision for male, it's much lower. The proportion on everything selected as class C1, class 1, the proportion of correct elements is much lower because you have much more errors in proportion. Then you can have other measures, for instance, equality of opportunity. It's one concept, but basically you give the same chances for male and female. So the chances that you are selected shouldn't be impacted by whether or not you're a male or a female. So in that case, we can look at, let's say, the bars for class C1. Those are the elements that you should select. And the chances of errors in this case, if you want equal opportunities for these elements that should be selected, is the proportion of this dashed bar below the zero line or the errors. So you would want to compare this proportion here dashed below and dashed below there with their bar. And you can see that for a male, among the good candidate that you should select, you have more errors. So you don't give the same opportunities, the same chances to the good candidate that you should select. A female have a bit of a higher chance of being selected. So that's also my point, is that you have different error rates and different forms of biases that you can see just with this simple graph. And depending on what kind of error is important or what class is more important, you can use this graph to make comparisons to see which model you should select. So for instance, here I see those three models, and depending on what, so the Bayesian classifier is obviously worst, we can forget about it for now. But if we want to choose between the tree model and the KNN model, if you're if it's about yeah, it depends the kind of errors that you can optimize. So for instance, you would give you'd have more of these errors here compared to this one. That's the only difference. So, well, but we can also see that on average for the KNN, it decreases all forms of errors in general. So there is an exercise, but for the sake of time, I'll give you the solutions right now. So the idea is now also one thing you can see with this simple graph is the number of elements you have in your test set. And here we can see that we have about 200 elements in each of the subpopulations, so each of the bar. And actually it's a little bit low. And I wanted to draw your attention to the fact that if you take another random sample, you might have different results. So that was the idea behind this exercise, but I'm just going to give you the solution. So the idea was to make different random splits into testing and training and see if we have the same kinds of results. So here I make a random split and I train my models on this random split and I plot it. And here I make another random split and I plot it with a number of, and it's again a small test set, and I can see do I have differences in the errors. Oh, I should look at this one. And a little bit. So here, this error here, these errors for the class 0 female, it's a little bit lower for the KNN on another split. And here I made other visualizations to show that with quite an extreme example. I even reduced the size of the test set and I used this Bayesian classifier, and with this visualization that I made another function also you could reuse. Here I show the results for different split, and I can see I have very different results. For instance, if you look at this bar C0 for male, here I have about 50 false positive, and here it has increased a lot more, and here I have a lot less. And it varies like this because the test set is small. And you can make more experiments with a bit larger test set, and here you have fewer variations. So it's just something to keep in mind before you go very much into details of comparing exactly how different are the errors between two classifiers. Beware of the size of your test set, which is something you might not see if you use error rates, which are ratios. And then if I make, so you have to also choose how much of your ground truth you'd use for test set. If you make it too little, you'd have a lot of variation. If you make it too high, you'd have less variation, but a lot more errors. And why is that? It's because then you'd have fewer items for your training set. And then your training set will tend to not make the right model for that. So that's in essence a demonstration of something called bias variance trade-off, very briefly. For an example with a large test set, when we look at this one, which is made on a small test set, we see for the tree and the KNN, this type of errors for class 0 male, they look equivalent. And here I took a larger test set, and here I can see that actually KNN was fewer errors than the tree. That's an example of like, beware of the sizes of your test sets before you really pinpoint by like an improvement of 1% or 0.5% of some error rates. Like, beware that it depends on your class size, how reliable this is. So now that we have seen this visualization, the last part of this tutorial is to use it in practice. And it's also a short notebook. And oh, let me see, there's a question. Yes, I can do this notebook very quickly. Here I have, again, my basic classifier, my data generator. Here is what we've seen with random variations. And now we can experiment with systematic variation. So now I have again trained those models on one training set that was balanced, let's say. And now I can use data that represents the real life. Let's say in real life, I have fewer female than male. And here I can see what kind of plot I would obtain. So you can see the proportions of what you'll end up in what you select. And will you have more male, a lot more male than female there because of your class sizes? So you can look at this kind of things. And here's the opposite, is when you have you have the same number of elements, male or female, but it's your class proportion that change between male and female. So let's say you're detecting fraud, and there's most of the elements are most of the elements are frauds, but there is a little bit more fraud for male than for female. And that's so you can see with the same models how the errors you expect in real life can be different depending on the proportions of classes and the proportion of subpopulation. And which leads to the exercise, but I am way over time. Sorry about that. So the exercise is, what if you were detecting fraud? Fraud are rare. What if you're selecting students? The good students are not that rare, but there are more female applicants. And what if you're detecting cancer and you expect more cancer among the female than the male? And you might end up making different choices. So for that, you can use this code as a toy exercise to manipulate the number of male and female and the proportion of each class per subpopulation, and see what kind of results you will get. And see what kind of classifier would work better. But because I'm over time, apologies, the first time I give a Python workshop.
No worries.
I hope you understood these basic concepts of the proportion of classes, the proportion of subpopulation impact the numbers you have in real life. And when you plot them to choose a model, you should use these proportions that represent what you expect in real life before you start to compare the proportions of errors and non-errors. Okay, so I can perhaps take questions. What is a good ratio for splitting the test set and the training set? That is a $1 million question. I can say that what you see in general is like 20% for test set and the rest for the training set. It depends how many elements you have. If you have a ground truth of 10 million elements and you take 20%, it's a lot of elements. And the issue of variance would be quite low. So the error measurements you'd get from this test set, even if it's a small proportion of your ground truth, are still quite reliable. But if you have a small data set, like the IRIS data set is awfully small. If you split it even just half and half, then at the end, the less you put for the training, the more over or under fitting is your model in general for every class and every subpopulation. So there is more an art than a science, but you have to find the right balance between having reliable error measurements and still being able to train your model. Any other question? Well, I can understand that that you're tired. Any remark is always welcome. It's the first time I give these workshops. If there is something that's not clear, it doesn't work, I'm happy to hear about it.
There's a compliment on the chat.
Yeah? Oh, thank you. I'm glad to hear. I'm glad to hear. Good. Yeah, don't hesitate to contact me later on also if you have some interesting problem you're working on. Is it an ethical practice to compensate the imbalance in class with opportunities? That's also a really good question. Let's say, yes, let's say you have fewer female applicants and you want to have gender balance. Yeah, that's this exercise here. Oh, sorry, in this case, you have fewer male applicants and you still want to have a good gender balance in your end results. Well, in that case, both classifiers, with these proportions, they are kind of gender balanced. But it is something you can think about. In that case, for instance, you have fewer male applicants and you want not to be sexist against male. It's good when it's their turn and not ours, right? You want not to be sexist against them. And you might say, okay, perhaps in my population of male, first there are fewer applicants and perhaps the ones that are considered good is also fewer because of historical biases. If you're selecting students for a nursing school, maybe we're sexist against them, men shouldn't be nurses. And so we have tended in the past to consider male were not good when they are good. So you end up having a ground truth where the good applicants are limited in your ground truth. But perhaps that's not, perhaps that's the fact, but it's not the actual truth. It's the truth as measured by humans, as labeled by humans. And even if it is, let's say, the truth, because they didn't get the same opportunities in the past, you can consider that even if they didn't get the same ratings as female, lower ratings on average, you still want elements that were classified as class 0, you shouldn't select. You still want to select more of them because you know you have a historical bias and you shouldn't repeat the past biases. So there's quite a debate. I'd like to keep having more and more is, should you use AI to repeat what's in your ground truth, or should you fabricate a desired truth? But short answer is when you see those errors, you can say, okay, actually, I want to have false positives for male in this case.
Okay.
Yes, question from Roger. Increase the number of training image by rotating them and resampling them from 100 to 300 pixel. Yeah, it is a good idea. It's a common practice. I think it's packed in many algorithms already. They do that for you, like the Swift features, they also do that. There is also something called data synthesis, data generation, and self-learning. That's also used a lot in computer vision. They might add some blurring, for instance. It's also part of the Swift feature algorithms, but they can add noise, add blurring, and duplicate the elements. But there are also ways to generate data points. You can train a GAN, for instance, on images and use the GAN to generate images for you. It's a fascinating chicken and egg problem. But then you can use your GAN to generate more examples that you have fewer example of. Let's say in your ground truth, you collected fewer darker skinned people, which was the issue in the example I presented in the slides. And you're missing these elements in your ground truth. Then you can use this data synthesis system to generate them. Amazing chicken and egg problem still, because if we have a system to generate the data, do we need an AI anyway? Because apparently
Isn't that a bit like resampling or oversampling?
It's different because when you oversample, you repeat the exact same data points. As let's say repeating the data points with some noise, let's say that would be different.
Mm-hmm.
I think for image classification is a little bit different because then you want to detect. So it's not only classify, but you want to detect. So then you do want, right, a lot of data. And indeed, you maybe don't have enough of one race with one function. So you want to.
Yes, and you have more natural ways to make variations of your data. There are typical forms of noise, different forms of noise that blur, contrast, color, balance, and so on. When you use tabular data with data points and blobs of them, you can add like a bit of random noise, but it's not as dramatic changes as you could do with images. Yes, question from Hannah. What do you do when the discriminating feature is continuous instead of binary? Wonderful question. Short trick, you discretize it. So you bin it into, okay, you split it, let's say income below 50K, above 50K. But that's a quick and dirty trick. But you can still plot populations this way. So you can see you can make masses of points among this axis, because you could also make a model of the errors you can expect depending on the income, but you'd have to train a model of your errors. I mean, a regression, basically. It's not done often, but I think for practicality or make it easier to check, both visually and mentally, but also statistically by having more data points in each bins. Binning is a quick trick. What is the best way to find out which feature caused the bias if it's not known beforehand? Yes, also wonderful question. And that's some of the research I want to work on. So I would say use explainable AI. So explainable AI, it's there's many families of metrics for it and techniques. Some depend on the algorithm, some you can apply for any algorithms, but there are a family of methods that will calculate the feature importance. Basically, you change a feature on your test set. So the basic method, you take a data point in your test set and you change one of these features. Let's say the age, this time you increase it, or the gender, you change it, you flip it. And you see how much it would impact your errors. So you take, for instance, all your female data points, you change just the label for male and you see if this would change your prediction. And the more it changes your prediction, the more you can say that explains my errors, in short. Libraries I'd recommend. I have put some additional materials here. let me introduce that. So there are these two tools that I find quite well done, but quite elaborate, and they use a lot of error rates. And I hope that this introduction will help you use those tools that are more advanced. Articles. So in terms of library with visualization, I think more could be done. I would add another link later on called Trust This ML. I'll show you. Yes, this one. So you can find prior work on inspecting models, and all based also to inspecting the errors, and they're very advanced visualizations as well. It's not for beginners. It's a lot of research papers, so I'll add that. I definitely recommend that you read this article. It's a short review by a great author, Karen Howe. She makes a wonderful job into summarizing different forms of biases I only touched in one basic form. And there is this comics on AI fairness that is wonderful, and it really goes deep into all the philosophical and ethical issues of AI fairness. You wouldn't see a false positive and numbers of errors in this one, just like amazing drawings, and it's fun, and it's going quite deep. And then you can also check these well-known cases. One is about text processing. So you have special biases in there and a few visualizations for that, for visualizing this. And then you can check these two cases with Compass, so the prediction of recidivism that was discriminating against Black people, and a bias in healthcare that was discriminating this time through a proxy variable. And you can check what visualizations they've used, especially the Compass analysis. The healthcare case, this is a very technical paper here, but for the most, there are visualizations in that too. But it will explain how they use a feature that looks innocent, so the money spent in your treatment, as a proxy, as to evaluate how sick you were. And the basic principle is that if you're sick, you had more treatments and you spent more money on it. So instead of counting all the treatments and the kind of treatments, they just like use the money. But it turns out that people who are poorer spend less money on treatment in the US. It's in the US where there's no social security. And so by taking this proxy variable that looks innocent, they ended up discriminating against the poorest individuals that were not spending as much and therefore not detected as sick. So they were detected later on when they were really, really sick, whereas the rich people had already passed the detection for the money spent sooner. And also because of social discriminations and issues, the Black people spend less money, or have less money, and therefore were not treated properly as well. Any other question?
I would say thank you very much, Emma. It's very interesting. It's also a lot of information, so thank you for that. There was a question about the repository. It will be there, and you will update with the other tool, right? You said there was the other group of visualizations.
That's I'll add this one link just right after this. Yes.
Great. So if nobody has any more questions, so thank you again, Emma. Thank you, everybody, for being present. We hope it was useful and informative. And please stay in touch with PyLadies Amsterdam. We have monthly workshops. Next month, we have a workshop on web scraping. And you'll find the recording on YouTube. During the coming days, it will be uploaded. So
Thank you very much for uploading the videos and for having me there and for all your good questions.
Yes, thank you for the questions. Also very, very interactive and very good questions. Adds to the topic for sure. It's yes. one of the most important topics, I think, indeed. With 2 lines of code, you can already classify something into 0 or 1, but what are you doing? So I think it's a very important. So thank you for presenting. Thank you everybody for listening and opening your ears to an important topic.
Yeah. Thank you
Yes.
so much. And yeah, if anyone wants to find out more about the topic, feel free to reach out to Emma or to one of us, and we'll connect you to her. Yeah.
Yes, please do. I have also our code if you want. Anyway, I'll let you have a good evening. Thanks again.
Yes.
Thank
Thank
you.
you everyone. Good
Have
evening.
a great evening. See you.
Bye.
Bye.
See you.